Welcome to another edition of Coonrod's Corner, brought to you by the Rogers Corporation. Today's topic, design decay. Why different test vehicle structures yield different decay values. Now, here's your host, John Coonrod.
Hello, my name is John Coonrod with Rogers Corporation. I am a technical marketing manager, and today I'm going to talk to you about design decay. Now, we have several different Coonrod Corner videos on this topic, and I invite you to get on our Rogers Technology Support Hub and look at some of those videos. Now, today specifically, we're talking about design decay and what happens when different test vehicles are used. And we have found over time, as well as our customers, that the design decay values that we generate with a microstrip transmission line can be different than the decay values from other test vehicles. And that does make sense, actually, when you put a little bit of thought into it. So I'm going to explain some of the concerns here and why you can get different decay values on the same material when used in different test vehicles. And to begin with, let me go ahead and talk a little bit about test methods. For test methods, IPC is one of the big industry standards, a group that makes standards for the industry. And IPC has probably, I think it's 12 different test methods for determining dielectric constant. And then there's also ASTM test methods, there's OEM test methods, universities have them. I have a book that has 78 to maybe 80 different test methods for characterizing materials at microwave frequencies. So there is a lot of test methods, and there is no perfect test method. Each one of these test methods have their own set of pros and cons, limits and capabilities. So what I'd like to talk about today is what happens when you're doing circuit evaluations and using different test vehicles. So to begin with, let me talk about a general category of these test methods between raw material testing and testing with circuit features. Shown here some information about different test methods being used, but my point really is showing it as two different categories. One category is testing the raw material itself, which is what we actually do here at Rogers. We make the raw material, the laminate and the prepregs, and we test the raw material. And those test methods are different than a lot of our customers that will take our materials, build circuits on them, and then how the circuit performs, they extract some of these properties, dielectric constant, dissipation factor. Now, what is determining these extracted properties, a dielectric constant dissipation factor for circuit, is actually dependent on the circuit fabrication process. So there's variables on the accuracy of determining these properties due to circuit fabrication. Now, on the other side of this, the raw material testing, those raw material tests are usually involving fixtures that clamp material in and then sweep through frequencies. But the accuracy due to how these test methods determine the dielectric constant dissipation factor are based on fixture variables, not circuit variables. So when you test the same material in a raw material test that has fixture variables that have an effect on the decay extraction compared to the same material being tested in circuit form that has circuit fabrication variables, you probably will not get the same answer. And it's because the test methods are trying to extract this information and having two different lists of variables that will impact them. Now, aside from these two different categories of test methods, there's also two different RF, I guess I would say structures or testing that is to be considered as well. So for test methods, there's usually resonant test methods using resonators, and then there's also transmission reflection test methods. Now, the transmission reflection test methods many times are using just a simple transmission line, and then you look at S parameters for transmission and even reflection. And what you get out of that is an extracted dielectric constant that's very wideband. So you can, in our case, we can actually get extracted dielectric constant numbers from about 10 megahertz all the way up to 110 gigahertz. Now, for a resonator test, that's a little different. Actually, what you're going to get is a extracted dielectric constant value at a specific frequency, so where the circuit actually resonates at. So you'll get discrete decay numbers at a certain frequency or multiples of that frequency. So depending on the test method, there are two different ways that you can evaluate that. Now, thinking about these different test methods and test vehicles, I want to show you a picture of several commonly used test vehicles for circuit evaluations, and gives you a little bit of a sense why you do get different values when you evaluate the material using these test vehicles. Shown here are several different test vehicles. These are all circuit test vehicles. The one on the top is a microstrip transmission line. I'm showing a 3D view. And then below that, I'm also showing a cross-sectional view across the length and showing some phase angles. Because normally what we do with a microstrip transmission line, we build circuits that are exactly the same but different physical lengths. Usually 2-inch versus 8-inch or something like that, a significant difference in length. And then we measure the phase angle. And when I'm talking about phase angle, I'm showing here if you had one full wavelength on a circuit, that circuit would have a phase response of 360 degrees. If it's a longer circuit, it's going to have more than 360 degrees. If the dielectric constant is higher and the wave compresses, you're also going to have more than 360 degrees. So this differential length method, where we have circuits to 2 different lengths, we are able to extract what the dielectric constant is by knowing physically what the difference is of these circuits. So that's one test method. And that's actually a test vehicle that we use most often for the microstrip differential phase length method. And that is what we determine, that test method is what we determine the design decay with that you see on our data sheets and product selector guide. Now below that are 2 different ring resonators. The first one on top is more of a standard ring resonator, except the feed lines are grounded coplanar waveguide. And I did that specifically to avoid unwanted resonances at millimeter wave frequencies, so I can test this at higher frequencies, and I have. And really what this is a ring resonator that is uncoupled, so there's a gap between the feed lines bringing the energy to the ring resonator, and there's a gap on both sides of the ring, so you have open feed lines that are bringing energy to the microstrip ring, and that ring will resonate at certain frequencies, and from that resonant peak you can actually determine the dielectric constant and maybe the dissipation factor as well. Now the ring resonator below that is a little different concept, and I actually like this more because this structure is less affected by normal circuit fabrication variables. And what it is basically a transmission line with a ring resonator set right next to it. So you have a transmission line, and what you would get would be a normal insertion loss curve of a transmission line, except where that ring that's edge coupled to it resonates. And where it resonates at, it's pulling energy out at a very specific frequency. So for the insertion loss curve, you get a little dip, or a suck out as they call it, at the point where that ring resonates at. And you can basically take that, put it into a field solver, and extract the dielectric constant based on where that dip happens at in frequency. The next circuit down is a series fed patch, and this is pretty common for millimeter wave radar. And these patch radiators are very small radiators that are basically resonators, but they also have a very small area that they are having these fields that are highly concentrated in that the radiation patterns come from. So this has very small areas that the material is being sampled in, whereas the ring resonator has larger area of the material being sampled for extracting the decay. And then the transmission line is a long circuit, so it's actually sampling the material much, much more, and actually it's going to be more affected by the copper surface roughness because you are basically sampling the circuit much more and much longer. Now the last test vehicle at the bottom is substrate integrated waveguide, SIW. I'm not going to talk about that much, but I wanted to throw that in because I've seen several different customers work with that for test methods. And you can use that as a transmission line and do transmission reflection testing, or you can use it as a resonator. Again, I'm not going to talk much about that because that's a really different technology than most of these other test vehicles. So let's move on and talk a little bit more about these test vehicles and how they behave. As you can see from the previous picture, these circuits have very different designs, and because of that, the fields use the material differently. And that's also a fundamental reason why you can get a different dielectric constant from these different test vehicles. So a transmission line, you have mostly fields between the signal plane and the ground plane with some fringing at the edges of the signal conductor. If the decay is higher, you have less fringing. If the material is thicker, you have more. So there's quite a variety of things in there, but the majority of the fields are between the signal plane and the ground plane, which is sampling the z-axis or thickness axis of the material. Now the ring resonators, they have gap coupling, and the first one I talked about had 2 feed lines with gaps on both sides of the ring, and each one of those gaps does contribute to the overall capacitance, and the capacitance can have an effect on the extracted dielectric constant value. Also, the amount of area that the ring resonator is evaluating is much less than these transmission lines. So you are looking at a little bit differences in how these fields are using the material and how they're reporting back the different things that will be extracting, different items that will be extracted for the dielectric constant. And then finally, these test vehicles, they also are very sensitive to copper surface roughness, of course, and that is the issue at the copper substrate interface. And a rougher copper at that interface will cause the wave to slow more, and a slower wave will be seen as a higher dielectric constant. So each one of these structures have different fields and how they're actually evaluating the material. Now the last one, the patch radiator, that actually has very strong fields right at the radiating edges. And the amount of material being evaluated is actually very little. It's right at the area where those radiated edges are. So the effects of copper roughness is going to be kind of a snapshot of what's going on just in that area. And the same with the material it's evaluating as well. So you can get a different decay value using these different test vehicles while testing the exact same material. Shown here is a comparison of several different test methods, all using the same material. As a matter of fact, these different test vehicles were built on the same sheet of material side by side. So there is no real material difference here. These are just differences in the extracted decay value per each of the test vehicles. Now the first one is the transmission line circuits. That is using the microstrip differential phase length, and that's a very wide band extraction for the dielectric constant. So we're going from about 1 gigahertz out to 100 gigahertz. And at 77, we get a decay value of 3.07. And then looking at the ring resonators, you see that their dielectric constant is a little bit lower. Ring resonator of 3.035, that's the ring resonator with the two gap coupled areas, and then the ring resonator with the through line with the ring coupled off to the side with one gap is a little lower again. And between these two ring resonators, you should see a little difference in the dielectric constant because there is a difference in the gap itself. And the gap coupling actually has an impact on the extracted dielectric constant. And then lastly, the series fed patch radiator at the bottom there has the lowest decay. And as you remember, this is sampling the least amount of material and the smallest area of the copper roughness. So when you think about what the fields are doing for each one of these test vehicles, they are actually evaluating the material a little bit different. And because of that, you are seeing differences in these decay values at 77 gigahertz. Now the material I'm using here is 5 mil RL3003G2 material. And that material is formulated to be extremely good at millimeter wave frequencies, and it does have a very smooth copper. If you did the same evaluation on a material that had rough copper, you would see much bigger differences because these different test vehicles that are evaluating the material and the effects of the copper roughness being included, the rougher copper is going to make the range of these differences of dielectric constant much greater, and that's just the nature of it. As you can see, these different test vehicles will give you different decay values, and that's actually normal when you put some thought into it. So each one of the test vehicles are going to be evaluating the material slightly different, and those slight differences will make a difference in the extracted dielectric constant. So that needs to be kept in mind when evaluating information on the microstrip differential phase length that Rogers offers, and then how it could be slightly different on the RF structure that you're using. This concludes this session of Coonrod's Corner. Thank you for watching.
For additional information and technical tools, if you're not already a member, join the Rogers Technical Support Hub and gain access to calculators, technical papers, and more Rogers Corporation informational videos. Rogers Technical Information is also available at your fingertips with the Rog mobile app, available for the iPhone, iPad, and Android devices. Check it out today.